Dear students, Assalamu alaikum. In our previous video, we discussed mass spectrometry, its introduction, and the instrumentation of the mass spectrometer. In this video, we will discuss what are the different type of fragmentations that occurs during mass spectrometry. So, although it depends on the type of ionization techniques, that different type of ionization techniques we can use in mass spectrometry, and that will be discussed in our next lecture. So today we will discuss what are the different type of fragmentations patterns in mass spectrometry. So the fragmentation may occur either through heterolytic cleavage, homolytic cleavage, which is also called as alpha cleavage, and McLafferty rearrangement. So these three kind of cleavage or fragmentation pattern were observed during fragmentation of the molecules in mass spectrometry. Mostly halogens, ethers, and alcohols perform or cleave homolytically or heterolytically. Alcohols sometimes perform cleavage due to loss of water. Ketones, aldehydes, carboxylic acid, and their derivatives usually occur or cleave through homolytically and also through Mc-Lafferty rearrangement. So we will discuss all these three type of techniques, and alkanes also, alkanes, alkenes or alkynes, we also observed that they cleave by homolytically. So first we will discuss what is the hydrolytic cleavage. So in halides, if we look at the example of ethyl, this is our propyl bromide, and one electron when removed from this bromine atom, it will produce a molecular ion peak, and we discussed in our previous study that what is molecular ion peak. So in molecular ion peak there is only one electron less than our molecule or compound, so it will give us a positive charge on the whole molecule. And when a heterolytic cleavage will occur, so both of these bonded electrons will be shifted towards the bromine, and the bromine, which is already positive or bromonium ion, it will get these two electrons and it will become a bromine free radical, and the positive charge will be shifted to the carbon atom, and we will get this carbocation and this branch which is positively charged. So this positively charged molecule will be detected by the mass spectrometer, and it will give us a peak at 43 gram per mole. Hydrolytic cleavage in alcohols. So here we have propyl alcohol. Again, if one electron is removed from this hydroxyl group, oxygen of the hydroxyl group, we will get a molecular ion peak, and this molecular ion peak, when heterolytic cleavage will occur, so both of these two electrons will be shifted towards this oxygen because of the electronegativity of this oxygen atom. So that's why we observe heterolytic cleavage, and in this case the positive charge will be shifted towards the carbon, and we get peak of this propyl group, and the hydroxyl will be a free radical. Cleavage in ethers. Here we have an example of propyl isopropyl ether, and in this case when an electron is removed from this oxygen atom, we get a molecular ion peak, and in this case we can observe heterolytic cleavage either from this end or this end. So from this end, this is, we call it first type. So in this case, when this heterolytic cleavage will occur, we will get this peak. We will get a peak of this propyl group, but this propyl group will be less stable, so the intensity of the peak will be low. However, from this side, the cleavage is more chances of the cleavage occur from this side because of this stability of this isopropyl group. So that's why this is called as 2, and when the cleavage will occur, we will get this peak where the positive charge is at the secondary carbon. But in both cases, we will get the same mass to charge ratio. Loss of water from alcohol due to gamma hydrogen. We also uh, observe the cleavage which is homolytic as well as heterolytic cleavage, and it is because of the gamma hydrogen. If it is present in alcohols, we observe this type of cleavage in which loss of water occurs. So here we have this molecular ion peak and we have gamma hydrogen and this hydroxyl group. So it will be heterolytic cleavage due to this oxygen from this hydroxyl group, whereas this bond will be shifted towards this and we will get a ring closing group here, bond here, which will close this ring, and this proton will be shifted towards this oxygen, and this oxygen when bind with this one, it will remove in the form of water. So in this case we will get this peak of the cyclocarbocation. Here we get a cyclopropyl and then loss of water. So this type of cleavage is also called as gamma cleavage, and this occurs in alcohols when they have gamma hydrogen. Now we will discuss what is homolytic cleavage or alpha cleavage in different groups. Let's suppose in halides when homolytic cleavage occurs, we will get a molecular ion peak by the loss of electron from this compound which is propyl bromide, and when the loss of electron occurs we will get a bromonium ion, and when homolytic cleavage occurs, this cleavage will occur from the alpha bond. So this is the alpha bond which is present between alpha carbon and beta carbon, and due to this homolytic cleavage, one electron from this bond will be shifted here and the other bond will be shifted here, which will get this ethyl group as a free radical. So this ethyl group as a free radical will give us no peak, whereas this, when this electron will be shifted here, one electron from this bromonium ion will be shifted here and we get a double bond here. So here we get a double bond and positive charge remain as it is, and thus we get a peak of this group, and this peak will be either absorbed at 93 gram per mole or 95 gram per mole depending on the uh, percentage isotope of this bromine ion. So this bromine, either it is 79 which is 50% abundance and 81 isotope also is 50% abundance. Therefore we get two peaks of one at 93 and the other at 95 gram per mole. In ethers, when homolytic cleavage occurs, the loss of electron will give us a molecular ion peak, and this molecular ion peak will give us two type of fragments may occur, like previously we studied in hydrolytic cleavage. If it occurs from this end, here we have alpha carbon and this is beta carbon and here we have alpha bond. So in this case, when homolytic cleavage occur, one electron will be shifted here and this electron will be shifted here. We will get this free radical peak, and this from this end to this end we will get a peak and a double bond will be here. So here we get a double bond and this will be positive ion peak which will give us a peak. On the other end, if cleavage occurs from this end, here we have alpha carbon and from this here this will be homolytic cleavage and this electron will be shifted here, one from here, and we get two double bond here, and this methyl group will be in the form of free radical will be broken down. So this is the free radical methyl group and we get this whole peak of this molecule. In ketones, when we get a molecular ion peak, we get a positively charged oxygen and in this case we get alpha cleavage either from this end or this end. So in this case this will be the alpha bond. This is the alpha bond because it is present between carbon and carbon. Although it is alpha carbon here, I am going to show you that alpha bond is different in halogens and carbonyl groups. In case of halogens or hydroxyl group or oxygen, we have this alpha bond which is present between alpha and beta carbon, while in case of aldehydes or ketones or carbonyl group, we have this alpha carbon. The same is alpha carbon is same, but the bond between two carbon will be here, and this will be the alpha bond. So in this case, the on both ends of the carbonyl group we have alpha bonds. Same is the here in case of carboxylic acid, but it is different in the other groups. So that's why in cleavage, when we observe alpha cleavage in ketones, we get cleavage from this bond or from this bond. When we get cleavage from this end, we will get this molecular ion peak with triple bond here with oxygen and a free radical of this methyl group. And when we get cleavage from this two second, and then we get a cleavage of this ethyl free radical, and this will we get a positive ion peak for this molecule or this group. Similarly, in aldehydes, when we get homolytic cleavage of this molecular ion peak, either we will get from this end or this. So in this case, when there will be cleavage from one, so we will get this as a peak. So this end will give us a peak with triple bond with this oxygen due to this positive charge atom, and other this will be a free radical. While in case of second, if the cleavage occurs from this end, we will get this hydrogen, and other will give us a peak which is M-1 peak because of one loss of only one hydrogen. Another type of cleavage in aldehyde is also occur in beta cleavage, which occurs from this end, and this is also homolytic cleavage, and due to this we will get although we will get a positive charge here, and we get this positive ion peak, or we get this positive ion peak. So we can get this type of cleavage also occur. Now we are going to discuss McLafferty rearrangement. In McLafferty rearrangement, there are three requirements which should be present, like pi electrons, non-bonding electrons, which are also called as lone pairs, and gamma hydrogen. If these three conditions are observed, these three conditions are present in aldehydes, ketones, or carboxylic acid or their derivatives, then we will get McLafferty rearrangement. So in McLafferty rearrangement, here let's suppose we have these n electrons, which are non-bonding electrons, are lone pairs. We have pi electrons, and we have gamma hydrogen, which is present at the gamma carbon. So due to these three reasons, we get McLafferty rearrangement. Same is the case in nitrile group. We have non-bonding electrons, pi electrons, and gamma hydrogen. If it occurs like this, we have aldehyde, but we don't have the gamma hydrogen, then there will be no McLafferty rearrangement in aldehydes, ketones, or carboxylic acid and their derivatives. So McLafferty rearrangement occurs in carbonyl compounds and their derivatives, like aldehydes, ketones, carboxylic acids, esters, amides, halides, nitriles, etc. So in aldehydes, if we have a gamma hydrogen, like here it is a gamma hydrogen, and then cleavage will occur from this bond, and it is the heterolytic cleavage, and we will get a double bond here with free radical, and this hydrogen will be shifted towards the oxygen, and this bond will be shifted here. So in this case, from this molecular ion peak, we will get neutral fragment of this R and this. So we will get a neutral fragment of the alkene group, and then we will get an enol group. So this is our enol hydroxyl group and this double bond. So enol group, and this is due to the aldehyde group we have hydrogen. So this will give us a cationic fragment, and the molecular mass or mass to charge ratio will be 44. In halides, if McLafferty rearrangement occurs, like halides, acid halides. So here we have halogen, and in this case the homolytic cleavage hydrolytic cleavage will occur from this, and this bond will be shifted here, and this gamma hydrogen will give us a hydrogen here, and this bond will be shifted here, and thus we get this neutral fragment, and this here we get enol with halogen, and due to this halogen the mass to charge ratio will be 44 minus 1 plus halogen. So minus 1 is due to the loss of this hydrogen. In ketones again we get here we have alpha, beta, and this is our gamma. So this gamma hydrogen will be shifted here, and this bond will be shifted here. Due to this we will get double bond here, and this carbonyl bond will be shifted here. So in this case we will get this fragment, which is neutral fragment, and here we get a positively charged fragment, or we can make this positive charge here. Also we can show here that this is our positive charge on the oxygen atom. So either here or here we can show it. So in this case we get only methyl group, so we will get 44 minus 1 plus 15 due to this addition of the methyl group, and we will get mass to charge ratio peak at 58. In acids again it will be breakage from here. This is our gamma hydrogen, it will be shifted here, this bond will be shifted here, and this bond here. So again we will get this molecular ion peak, and we will get a fragment of mass to charge ratio of 60 due to hydroxyl group. Now in nitriles again is the case. Here we have gamma hydrogen, so this gamma hydrogen will be shifted towards this nitrogen due to lone pair of the electrons, and this bond will be shifted here, and this bond towards this. So in this case again we will get this type of positively charged fragment with mass to charge ratio of 41, and here we get R, and this will get, here we get double bond, which will be a neutral fragment. So neutral fragment of will be like this. So it will be like this, which will be a neutral fragment, and it will give us no peak. So this is our neutral fragment, and it will give us no peak. There are some other examples of some other functional groups we can also observe, like aromatic compounds. So now we are going to discuss depending on the different functional groups. We already discussed three type of fragmentations, that is homolytic, heterolytic, and McLafferty rearrangement. So here we get some special groups, like here we have carboxylic acid, and the cleavage is due to homolytic. So due to homolytic cleavage we can get two type of fragmentation. First, like here we have this homolytic fragmentation, and we get this, no, first if we get this one, so this is our first, and in this case we get this hydroxyl free radical, and this bond will be shifted here, and this oxygen bond this electrons from oxygen will be shifted here, and we get this oxonium ion. So this will give us a peak and hydroxyl free radical. In second case, so second case is observed here. In second case it is from this end. So from this end we will get this positively charged fragment, and this is our this is our positively charged fragment, and this bond will be shifted here, so it can be like this carboxylic group. Cleavage in aromatic compounds. For benzene, only one electron is removed from the whole ring, and we get only one peak. So this is molecular ion peak. We will get no fragmentation of this benzelium ion. So in case we have some attachment or substituent attached with the benzene ring, so we get other fragments due to this homolytic cleavage. So this homolytic cleavage, we will get this benzyllium or benzyl cation fragment, and this benzyl cation fragment can rearrange and we get this type of tropylium ion. So this is called as tropylium ion, and we get mass to charge ratio of 91. So this will be rearranged in the form of tropylium ion. Now we discuss fragmentation alkanes, alkenes and alkynes. In alkanes, usually we get the loss of methylene group, and we get this molecular ion peak with -14 due to this methylene group. In branched alkenes, fragmentation may occur due to at the branching. Here, like here, it is branching and we get homolytic cleavage from this bond, and then we get this type of molecular ion peak, and this will be a free radical, this R. In alkenes, we get cleavage from this. Here we have this alpha carbon and we will get cleavage from this. This is also a homolytic cleavage or alpha cleavage, and we get this fragment which is positively charged, and this is our free radical. In alkynes, same is the case. We will get this from this alpha carbon, we will get this homolytic cleavage, and then we get this propyne cation and R free radical. So in alkanes, alkenes and alkynes, we get homolytic or alpha cleavage. So thanks for watching my video. In our next video, we will discuss different type of fragmentations. In our next video, we will discuss different types of ionization techniques in mass spectrometry.